Video is another example of a linear system of differential equations. And let's leave this one kind of a mystery, unless you look at the title of this video, which maybe you already have. Let's see what happens when we try to solve this system. And I think I will make it an initial value problem. Let's say that y of 0 is 1, negative 1. All right, so there's A. The determinant of A is going to be 12 minus negative 8, which will be positive 20, non-zero. So as usual, the origin will be the only equilibrium point. The trace is going to be 2 plus 6. That's 8. And therefore, the eigenvalues can be found from the usual equation. Lambda equals t trace plus or minus the square root of t squared minus 4d over 2. So that'll give us 8 plus or minus square root of 64 minus 80 over 2. 4 plus or minus square root of negative 16. Many of you probably already know what to do in this situation. The square root of negative 16 is 4i. Where I is called the imaginary unit. It's defined to be the square root of negative 1. But wait a minute. Some of you, perhaps, it's possible, I suppose, you've maybe never heard of the imaginary unit. And for those of you who have, which I imagine is most of you, you may have always wondered, what is it really? Does it really exist? I mean, you can't take the square root of a negative number, can you? Well, for the sake of doing math and getting answers in nice ways, essentially we're going to assume we can. You can mathematically construct the complex number system, which consists of numbers of the form a plus or minus b times I, where a and b are real numbers. Define how to add, I guess I'll just say a plus bi, where a and b are real numbers. Define how to add, subtract, multiply, and divide those kinds of numbers where I is the square root of negative 1 and a and b are real numbers. And you can define this number system in a way that's very satisfying. It's very complete. It satisfies what's called the field properties of a number system. And, well, it'll turn out to be useful for us. We'll see. So we can avoid truly philosophical questions and just treat it as something that we construct. Square root of positive 16, of course, is 4 when we take the positive square root. So when you've got negative 16 and you take its square root, you think of that as square root of positive 16 times square root of negative 1, and that's why we write it as 4i. So those are our eigenvalues. Two complex numbers, 4 plus or minus 2i. Let's try to find the corresponding eigenvectors. What will happen? It seems like it might be kind of a mystery where this is going to lead us. Let's take the first eigenvalue, 4 plus 2i. Remember, what you need to do is go back up to the matrix, subtract lambda from the upper left and lower right entries. Don't subtract it from the upper right and lower left. Put the x and y in there. Those are going to be your coefficients of a homogeneous equation where 0 is on the right-hand side. So I've got 2 minus 4 plus 2i times x plus 2y equals 0, and negative 4x plus 6 minus 4 plus 2i times y equals 0. If you compare the matrix at the top with that system of equations, you can can see that I have done what we usually do, though it's more complicated looking. This first one simplifies to negative 2 minus 2I times x plus 2y equals 0. The second one would simplify to a negative 4x plus 2 minus 2I times y. Those equations don't look redundant, but they actually are. I won't take the time to check that here, but let's just assume they are. Instead, what I'll do is I'll take that equation and do what I usually do, solve for y in terms of x or x in terms of y. It'll be easier, it looks like, to solve for y in terms of x. Divide everything by 2 and put the negative 1 minus I times x on the right-hand side to get positive 1 plus I times x on the right-hand side. Evidently meaning that our corresponding eigenvector, if I take x to be 1, y is 1 plus I. So not only do we have complex numbers floating around here, but we also have complex vectors. It gets scarier. Just be patient. Take a deep breath. You can do it. But where do we go from here? We might wonder if we take this complex lambda and write e to the lambda t times this complex vector v, whether it is a solution or not. E to the 4 plus 2i times t, that complex exponential, times this vector, is that complex valued function a solution? I won't take the time to do it, but you should. Maybe you should even pause the video right now and check that this really does solve the original differential equation if you plug it in for the capital Y. In other words, take this matrix and multiply it times this vector. You could take this complex scalar and distribute it through the parentheses. And also differentiate it and check that you get the same thing. If you're going to differentiate that, it really does work the same way as with real numbers. The chain rule will be needed to bring down this extra factor of 4 plus 2i in front. And if you use the fact that I is the square root of negative 1, so that I squared is negative 1, and make those replacements anytime you see an I squared as you simplify, you should see that it really does work. So let's assume it does work. How is it any good? I mean, we do want real answers. We want a phase plane. There's no complex numbers in the original problem. I could certainly make the vector field and the corresponding direction field and get a computer to draw in some solution curves. That seems like it should be something that I can do, and you could try that. So how does this complex number have anything to do with it? The key is a couple of things. First of all, we need something called Euler's formula, which is one of the most wonderful formulas in all of math. Euler, as we've seen before with Euler's method, is spelled E-U-L-E-R. We go back to black here. Here's Euler's formula. E raised to the I times theta power equals cosine of theta plus I times sine of theta. That's very strange looking if you've never seen it before. How could an exponential function be related to trig functions? Not sure how much time we're going to have, but at some point I'm going to show you that you can derive this if you assume that the infinite series, Taylor series expansions for the exponential function and the trig functions do work, especially for the exponential function when you plug in I times theta in place of x. And you can verify that. But how is it relevant to us? trying to use the computer later on, hopefully, and I don't want it to time out on us. How is this relevant for us? Well, this thing can be thought of using properties of exponents as e to the 4t times e to the I times 2t. And so what we can do is we can think of the 2t as like the theta down here. Treat it like the theta down there. And what will happen then, if I do that, is I'll get e to the 4t times cosine of 2t plus I sine 2t. Don't forget my vector over here, 1 plus I. I can distribute the e to the 4t through. And it might also be helpful to split this vector up into two pieces. Like this, as the vector 1, 1 plus I times the vector 0, 1. Does that make sense? Hopefully. But I can write that vector that way. What I'm going to do with this is I'm going to rewrite it now. I'm going to multiply this expression in the parentheses times this expression in the brackets. Essentially, I've got two binomials involving imaginary numbers. I'm going to essentially do the FOIL method. I'm going to multiply first times first, outside times outside, inside times inside, and last times last. Before I do that, though, let's think about which of those products are going to give me real quantities and which will give me imaginary quantities. First times first gives me a real quantity because there's no i's there. Last times last will also give me a real quantity because I'll get an I squared involved, which is -1. It's the outside and inside products that end up being imaginary. So, with that in mind, I'm going to do this product in my head, keeping the real part together and the imaginary part together. I'm going to do first and last and keep those together. E to the 4t cosine of 2t times 1, 1. That's the first times first. And last times last, the I squared gives me -1, so I get minus e to the 4t sine of 2t times the vector 0, 1. That's my real part of this function. What about the imaginary part from the outside and inside products? I'll just put the I out in front. Outside times outside is going to give me I e to the 4t cosine of 2t times the vector 0, 1. And inside times inside gives me I times e to the 4t sine of 2t times the vector 1, 1. And then I can group these together into one vector here. I can write this as e to the 4t cosine of 2t minus 0 on the top, and then on the bottom I've got e to the 4t cosine of 2t minus e to the 4t sine of 2t. And do the same thing with the part to the right of the I. Group those into one vector. Once again, at the bottom it's going to have two terms. It'll have an e to the 4t cosine of 2t plus e to the 4t sine of 2t. I'm running out of room here. And the top is only going to have one term, e to the 4t sine of 2t. Sorry if this is kind of a mess. You can try rewinding and rewatching it if you can't quite follow it or can't quite see it. Hopefully that's big enough. The writing's a little bit messy. Here's the amazing thing. All these complex numbers going on, the amazing thing is that this function, that vector value function, the real part, and this one without the I, the imaginary part that's next to the I, both are real solutions to the original differential equation, not complex solutions. And moreover, they are linearly independent. So if we take an arbitrary linear combination of these, we'll get the general solution. And for the sake of making it look a little nicer, I think I'll also factor out the e to the 4t's in both cases. So I'll have an arbitrary constant k1 times e to the 4t times a vector involving cosines and sines. I've got a cosine of 2t minus sine of 2t on the bottom, and a cosine of 2t on the top, plus an arbitrary constant k2 times e to the 4t times this other vector without the I. Don't put the I in there anymore. E to the 4t cosine of 2t plus e to the 4t sine of 2t on the bottom, and e to the 4t sine of 2t on the top. That's your general solution, your real valued, well, the components are real valued, general solution. It is a vector solution, though, when you put it together. I'm back again in my office. Another mistake. Shaking the computer, too. If you look back at the second vector in that formula, when you go back to the video, you'll notice that there's a mistake. And I never fix it. I don't know why I didn't notice it. The e to the 4t is both outside of the vector in the second vector and inside the vector. It should just be outside. There shouldn't be any e to the 4t's that are inside that vector. You don't want to have two factors of e to the 4t in that general solution. So that general solution is wrong. You should erase the e to the 4t's that are inside the second vector. The second function, or the solution to the initial value problem that I eventually derive is right. The coefficients, the k1 and the k2 for the initial value problem, you'll see do turn out right anyway. But you should change the general solution. One thing you'll also notice that I forget to mention later on is I'll say the solutions spiral away from the origin, but I forgot to emphasize that the origin is a spiral source, as the title of this video says, for this particular system, and that should be labeled in the phase plane. I'm not going to take the time in this video to verify that the real and imaginary parts here that I've underlined in blue definitely solve the original equation. You can see that they're not multiples of each other. They're not scalar multiples, and in fact that would be true, but they're not scalar multiples for any value of t. I'm not going to take the time to verify that here. Maybe in another video I will. You should certainly read it and be able to understand it and be able to reproduce it on an exam. What I will take the time to do now is to finish the initial value problem, to also draw the phase plane, and then to tell you something amazing. So the initial value problem was that y of 0 was 1 comma negative 1. You might think, oh no, it's going to be crazy trying to solve an initial value problem involving this function, but it ends up pretty nice. When t is 0, lots of things go away. E to the 0 is 1. That's a 1, that's a 1. Sine of 0 is 0. This goes away, that goes away. Cosine of 0 is 1. That becomes a 1, this becomes a 1, this becomes a 1. When you plug in t equals 0, you see that y of 0 is k1 times 1 times the vector 1, 1 plus k2 times 1 times the vector 0, 1. You're going to set that equal to the initial condition, 1, negative 1, and solve for k1 and k2. The system of equations you get is pretty simple. k1 is 1, k1 plus k2 is negative 1. So k1 is 1, and k2 will be, let's see, that's a 1 there. That'll be negative 2. And then just plug that back in to this equation to come up with that particular solution to the initial value problem. And you should certainly be able to look at the components. little x and little y and draw their graphs and see what they look like. What about the phase plane? Well, first of all, the origin is the only equilibrium point. Because we've got complex number eigenvalues and eigenvectors, there are actually no straight line solutions. When you've got complex eigenvalues with a non-zero real part, those are the eigenvalues, 4 plus or minus 2i, the real part is 4, non-zero, the solutions are going to spiral. If that real part's positive, they'll spiral away from the origin as t increases, which should make sense if you think about the general solution. Certainly this function should get very big as t goes to infinity because of the e to the 4t. And the components oscillate because of the trig functions. So you end up getting solutions spiraling away from the origin. Another issue, though, is do they spiral clockwise or counterclockwise? The easiest way to think about that is to imagine plugging in, say, the point 1, 0 into the vector field, which will give you the vector 2, negative 4 out, the first column of this matrix. The vector 2, negative 4 points, if you put it at its base at the point 1, 0, it points downward into the fourth quadrant. That's going to mean that the solutions have to spiral clockwise in this case. So your generic picture for this kind of situation looks like this. You don't have to get the exact shape right. Just get the right kind of spiraling outward and the fact that it's clockwise in this case instead of counterclockwise. And that'll be good enough for the phase plane. You could certainly get your calculator or Mathematica to draw it better, and particularly you can draw the particular solution to the initial value problem. That was one thing I was going to spend the time to do here on the computer, but I think I'll save that for another video or perhaps something else. Instead, we need to finish off, this is more important of course, with something really cool. If you're ever captured by aliens, and they take you onto their spaceship, and they say, we'll let you go, of course they'll talk in English, we'll let you go if you tell us the most beautiful equation in the universe. Well, guess what? Today's your lucky day. I'm going to tell you the answer. There are some people who write this differently, but I like writing it like this. E to the I pi plus 1 equals 0. Some people write that in the equivalent form, e to the I pi equals negative 1, but I like writing it like that better because I think it's a little bit more beautiful. Why is this the most beautiful equation in the universe? It's because it's got the 4 most fundamental numbers in it. 0, 1, pi, e, and I. Those are the five most important numbers in the whole universe. And that includes C and H bar for you physics people. You know, those are not numbers, they're physical constants, so they're not true numbers. Their values depend on the units you choose. So these are the 5 most important numbers. Where does it come from? It comes from Euler's formula. E to the I theta equals cos theta plus I sine theta. If you replace theta with pi, you get cosine pi plus I sine pi, or negative 1 plus I times 0, which is negative 1, and then you just add a 1 to both sides of the equation. In another video, I will derive Euler's formula for you.